So, today is the third lecture of module 1 of the lecture on waves in space time and propagation. We are discussing properties of space time, though there are several points that come under this heading of properties of space time. First, what comes is that description of the space time and the invariants, those are generated in terms of these variables, those describe the space time. As it turns out that this space time symmetry follows some certain symmetry groups transformation property, and the group generators actually follow a algebra, and from the algebra one constructs the transformation laws for the quantities those are involved, and this transformation can be generalized to the structure of the Lorentz transformation, and they are essentially of two types. One is rotation and another is boost, which comes under the heading OPLT, orthogonal proper Lorentz transformation. Then what arises is what you call invariance of quantities under these transformations and what are called covariance, and what are the observables, those remain invariant under these transformations. What are the observables, those undergo a transformation and are called covariant Lie transformed observables. So, to give you the example, in typical Euclidean geometry, if two points are stationary, then the distance between them will not change. And this distance remains the same irrespective of the coordinate system that we choose. So, this is something like an invariant of or invariance of the system under coordinate transformation between 2 points, those are. But however, if these 2 points are not stationary and they follow certain law of evolution of their coordinates with time, then this invariance will not be maintained. Now, when we talked about this invariance and covariance under a transformation, there is certain description that we have not covered, and these descriptions are called the type of transformation. Those can be active and those can be passive. To give you an example, if the physical position of points that is and those are under consideration, they change relative to a coordinate system under this transformation, then it is called a active transformation. And if the reverse happens, that is the points are left fixed even if we change the coordinate system, they are usually termed as passive transformations. So, it depends on the system that is under consideration and how the variables are behaving under these transformations. That defines a passive transformation or an active transformation. For instance, if we consider the sun, and sun is much heavier than the planets that orbit around them. So, sun's gravitational field can be considered to be something which is constant. If we move from one planet to the another planet, and during our motion or movement, we carry the coordinate system with us from one planet to another planet, then the coordinate system has actually undergone a transformation, but the gravitational field that is under consideration has remained the same. So, having described the nature of the transformations and the invariance or invariance in Galilean system or coordinate system, we come to the description of space time for a relativistic coordinate system or Minkowski space. Usually, for this particular class of systems, it is not just the space, the time is also involved, and in general, any point in this space-time picture comprises of 3 spatial coordinates and 1 temporal coordinate. So, if we start from a system that is defined by these 4 parameters, 3 spatial coordinates and 1 temporal in a particular frame of reference, and there is another frame of reference. That particular frame of reference is called the primed frame of reference, and it is also defined by a set of 4 coordinates, 1 time and 3 space. Then these 2 coordinates are related to each other by a transformation which is shown here in equation 1. So, the primed coordinates transform by the a multiplicative factor which has a metric structure 2-dimensional with 2 indices mu and nu times x nu, and this matrix lambda mu nu, which is actually corresponds to different elements depending on whether the values of mu and nu are taken to be 0 to 3 or 1 to 3 to 4, are called the transformation matrix for the space-time system, and it is also called the Lorentz transformation matrix. A variable usually is called a covariant variable under certain transformation when the structure or the tensorial structure of that variable under the transformation retains its structural form. The variables need not be the same, but the structure of the tensorial form will be the same. Then this is usually called a covariant transformation, and on the other hand, if it so happens that the variable under consideration retains its original variables after the transformation, or the quantity under transformation does not undergo change after this transformation, then we call that particular variable a invariant variable under the transformation that is under consideration. As we move along, there will be examples, and these examples will actually exemplify the definitions that we have provided a while ago. Now, let us say that we define two space-time points in two coordinate system, primed and unprimed, from their respective origin. So, in one system the distance is x and the other system the distance is x prime. Then what invariance tells us is that the contraction of x prime mu with x prime mu covariant and x mu contravariant with x mu contravariant are the same. That is, in other words, the space time interval in the primed coordinate system and the space time interval in the unprimed coordinate system are same. Now, a while ago we have defined the route to go from primed coordinate system to the unprimed coordinate system in terms of the Lorentz transformation matrices. And I assume that the audience is familiar with the operation of raising or lowering the index on a particular variable by the Minkowski metric eta mu nu. Then what can be done is what is written in equation 3 to relate the Lorentz transformation matrices lambdas with the Minkowski matrices eta. So, to read it out, the content of the third equation, that is lambda mu alpha eta mu nu all covariant and lambda nu contravariant with beta covariant should be equal to the Minkowski matrix eta of alpha beta. Now, this transformation law which you have written in equation 3 actually follows from equation 2 when you use the Lorentz transformation properties of x prime covariant mu and the x prime contravariant mu. We can expand this Lorentz transformation matrices lambda of mu alpha close to the identity. So, what is the identity element? The identity element is delta mu alpha. That means, if we contract it with another vector having one index, it just remains the same, plus an infinitesimal transformation that we have defined by epsilon of mu alpha. At the moment, when you have written this particular relation 3, this is the most general relation, and the infinitesimal transformation of lambdas, that is the Lorentz transformation matrices near the origin that we have written, are also most general possible transformation. We have not imposed any condition on this particular matrix that we have defined by epsilon of mu, that index is contravariant, and a index alpha which is covariant. We can raise or lower the indices mu and alpha by suitably contracting with the metric tensor eta mu nu here at this stage, or in most general case is a metric tensor g mu nu, but their form just remains the same. Now, if we use this particular form in equation 3 and we insist that we retain terms those are linear in epsilon mu alpha, the higher order terms are thrown away, then it so happens that epsilon mu alpha gets related to epsilon alpha mu with a multiplicative factor of -1. So, as it stands that for infinitesimal Lorentz transformation, this transformation matrix epsilon mu alpha is an antisymmetric tensor in the indices alpha and mu, and being an antisymmetric tensor of two indices mu and alpha, it immediately tells us that if these indices alpha and mu happen to be the same, then these elements should be equal to 0, and if these elements are different, then they should be non-zero. So, let us now try to get a estimate. In general, mu or alpha, they can vary between 4 numbers, either 0 to 3, or in the other case between 1 to 4. It depends on the convention that one is using. Nonetheless, general observation would remain true. So, altogether each matrix depends on 16 elements. 4 times 4 is equal to 16. And out of these 4 elements, diagonal elements, out of these 16 elements rather, the diagonal 4 elements are 0. So, what remains are 12 non-zero elements, out of which the elements with indices I j is related to the one with indices j I, that is permutation of these indices with a negative sign. So, what happens then is out of 12 we are left with only 6 elements, those we need to know. To describe this Lorentz transformation or infinitesimal Lorentz transformation. So, the matrix now has only 6 unknown quantities, those are required. So, this is the details about the infinitesimal Lorentz transformation. Thank you.